Hello, everyone. Thank you for inviting me to speak. I'm Laptev, and I'm going to talk about understanding and generating actions. Given the topic of today's workshop, let us first talk about compositionality. So we know that objects and scenes are composed of parts. But what about actions and longer activities? So here is a few videos showing examples of opening bottles. And while these examples are somewhat extreme, you can imagine that actions can be composed of lots of different objects, tools, and motions. And the execution of actions can be very different, even in normal settings, because our scenes, which we are surrounded by, they are often different, and we have to find new ways how to perform actions. So while these examples were showing a simple action performed in many different settings, next example is showing a chair assembly time lapse. And in contrast to previous sequences, here the actions are actually quite simple, of screwing and attaching the table, where the whole structure of this video is very specific and complicated. And one can imagine that if putting these in the not correct order, something wrong may happen, and indeed sometimes it does happen. So if you do not follow instructions well and follow the order of actions, then the chair may not look like a chair. So in conclusion, so what we see, what I'm trying to convey is that actions and activities are indeed highly compositional. And they are compositional in space in terms of objects and motions, which can perform to achieve the goal, as well as in time, where the temporal structure of primitive actions plays a crucial role to achieve the goal. So how can we address this diversity and compositionality? In my group, we try to approach these questions from two parallel and related directions. The first direction is about analysis. This is a pure vision task. We try to analyze instructional videos. Instructional videos, and it will describe shortly, they are goal-directed activities, for example, changing a car tire, and therefore they are composed of actions which are necessary to achieve the goal. And the second direction is robotics, where we try to learn robots perform a task which is typically composed of many different actions. So in the rest of this talk, I will describe a few works we've been doing in these directions. And first line I will describe is about instructional videos. Instructional videos, for all of you have came across and watched some of them. First, here's the instructional videos, a person showing how to change a car tire. These videos are made by people for people, and they are narrated, so they are provided. Videos provide also text track. This video is for many. There are different versions of the same task performed by different people, and also not for one task, but actually for thousands of tasks, which I will show you later. So this is a financial reach and data. Also, as I said, it's not just video data, it's also data which comes with transcripts which are aligned with the videos. Okay, so this is the data which I'll be mainly talking about in the first talk. So what can we do with this data? So one problem which we try to address in a few years ago is to find out what are the key steps of the task. they are given not one but many videos of changing character. We would like to several outputs. We would like to discover automatically by now what are the main steps of changing character. We also would like to learn visual and linguistic representations, and we would like to temporarily localize these actions in video. Okay. So the problem is not trivial. Starting from the text can be varied a lot. As you've seen already in the motivating slides, the visual appearance of actions can be very different. So here the problem was formulated as a discriminative clustering. So the text was clustered together to find out what are the typical action steps, or given the text, the steps from the text clustering. So we are also applying the clustering to the domain. So in both cases, for text clustering and for video clustering, the key assumption is the order. So we assume that the data sets are in the same order in all videos. This may not be always true, but in most cases, you find out that this is a valid assumption, at least the set of tasks which we have considered. So in a very short, so it's a clustering problem, so it's not supervised classification problem or learning problem. So we are not, what we are trying to resolve is both the classifiers for individual steps or actions, as well as the locations where they have a video. The locations in matrix C, and we probably classifiers the matrix W, multi-class classifier, which is acting on some feature which will be seen and works on other features. Right, and so the main goal in this paper was to formulate it as the discriminative clustering with constraint of the order, and the order is provided by transcripts. I'm not going to stop to explain many details in the paper. So this is just an illustration of one work which worked on with this type of videos. So these are test videos, or these are videos where the algorithm automatically has discovered the steps of character. So this work was related just on 5 tasks, and they were treated independently. So, we call it lunch, character, jump character, CPR, and making coffee. So of course, there's many questions remain. For example, how to scale to tasks, how to improve the action summary, and how to learn appropriate user representations. And these are questions which I'm going to briefly talk about. So first, yes, you want first to scale to tasks. For this, there's just practical issue. Our training is unsupervised, so we can actually apply it to many tasks. However, to emulate if the algorithm has learned something useful, we do need conditions. So we have collected so-called cross-task dataset. So here's a comparison. This work was published in ECCV2020 CAMP. So since then, there are new datasets, I'm going to show it later. So cross-task at that time was the largest dataset, but also it had 10 connotations and was not limited just to booking actions as some other datasets. So yeah, it has a mix of domains, booking, gardening, car repair. And it also has a set of tasks which we call primary tasks, where we have a vision of precise implementation of actions and labels of actions. And so also like related tasks are not completed, MIL-NCE unit, they actually help to solve the problem. So primary task in total 18 of them, and few hundreds of videos for each one. And again, so this annotation is only used for evaluation. This time it's not used for any. The goal is to do everything unsupervised or self-supervised, provided the videos and transcripts. So maybe I didn't mention it. So why do you want to do it unsupervised? Given the motivating videos we see in the beginning and the diversity of activities in terms of action, in terms of tools, motions, temporal compositionality, it seems just very hard to do things to assume that we will ever have enough manual supervision to do supervised learning. So we would like to avoid any sort of manipulation, or at least to keep it to the minimum extent. So now the assumption in this work is that once we grow the scale, so we will eventually have things repeating on the level of individual actions, but also what we call ER components. So assuming, if you look at language, so we can assume that the action usually consists of a verb and a noun, for example. So, for example, pour egg, add sugar, whisk mixture, and we could treat the pour egg and add sugar as just units of steps. Here in this work, we also try to decompose them into components. Component, one component would be another component would be mixture. And what's nice about it is that when we go to other tasks, making pancakes or making lemonade, see that these components, they reappear in a new configuration, pour mixture or pour water. But if we train all components together, from all videos, from all tasks, the task hopefully should start helping each other. And the performance should increase as we go for more and more tasks. And so here is what I mentioned for the primary task and related tasks. So related tasks are collected exactly for this purpose, to show by increasing the amount of data can we get a benefit for our primary task where we have annotation. So here is the model for this work. So it's a simple linear model. You can see it as an extension of the model which I've shown before. So it's still discriminative clustering model. However, it mix the components and spirit functions across different tasks. So this is the main idea of this paper. So there is a mixture matrix A, which is in our case predefined. It could be obtained automatically in some way. We learned that in this case we simplified our tasks a bit, and it is provided manually, but then the G, which is the component classifier, this component classifier is shared across all tasks. So it is learned as well as the lineage, which assigns the individual time steps of the video to the actions. So it's a discriminative clustering game where we update the classifier for components, and then we recluster, so we obtain a new solution for the matrix Y, iterate, and obtain the solution. So let's jump to results. So what we see in this table, we see a few different things. So first column is unshared primaries. we just train, primary means that we just train on the 18 primary tasks, and unshared means basically we do the same as in the previous verification process. So we are not doing any sharing, we are not benefiting from by earning information across tasks. Shared primaries, we do sharing between tasks, but still learn just on the 18 primary tasks. And shared primary task related means that we learn on all 83 tasks we have in our dataset. The line-wise, so we compare two things. One is the step-based classifier, and one is a component-based classifier. Step-based classifier would be temporary retreat with mixture as a unit, as one action, we don't decompose it. Component-based is where retreat whisk and mixture as two different entities, two different components, and we learn them separate, we learn them, and that they have identical. So a few things to note that first, going home-wise, so sharing really helps, and it does help also with the tasks. So this is nice. It means that the more data you put in some performance as proof, and we can imagine just scaling up the data set easily because we are not relying on the manipulation. And so line-wise, you also see that there is improvement that we go from action classifiers to component classifiers, so we break actions into components in terms of verbs and nouns. So this is nice. Also, yeah, on the right, there is also a comparison to the hardware. We show the improvements. Another good thing with this method is that it can do zero shots. So as it learns components, so say from previously seen tasks like cut steak or cut tomato, add cherries to the cake. As it learns the components from these tasks, now it is also able to interpret the new tasks with the steps which have never seen before. For example, adding strawberry to the cake. So it knows already what is the cake, what is the strawberry, what does it mean to add, what is a strawberry, and it is able to interpret these actions correctly. Now, what you see also right is that the more tasks we give to the system for training, the performance does increase, and that's exactly what was the purpose of the method, to show that we algorithm of zero shots. So we have red line corresponds to feedback automation outside so you would see the examples of as strawberry cake training, and the blue curve means that we have never seen it in zero shot. So the blue curve approaching the one, which is a good sign. Okay, however, so the numbers actually, as you probably noticed, are not huge, so it's now 10%. It means that there is still lots of room for improvement, even if we hop. So let's see what else can we do. So here is the work which actually will be presented at ECCV this year, and it tries to learn actions from temporal model notation. So what's the motivation for this work? We want to, so here we don't even want some to discover steps of particular actions. Here we would like to have something very generic which says this interval of video is actually an action or not. What is an action, what is not an action is may not be very clear for us we assume an action to be which is meaningful for achieving a goal. And so, for example, people talking would not be an action. Usually, in our videos, the talking is not important for achieving an action. However, putting, for example, in a CAMP would be a meaningful action, which is required for data, such as making data. And again, so we don't want to, in this case, don't want to have any supervision here in manual annotation. And in this case, we are not even looking at narrations, we're just looking at the instructional videos as they come. So here, behind the method is we would like to, by looking at these examples at the bottom, can make a quiz and ask what is given. So all these frames are from the same video. So if you look at the frames, 2 frames on the left, the question is, can you figure out the order of these frames in the original video? Does the leftmost frame come before the second frame where the person is looking up, or after? And the same question for the last 2 frames on the right. So what is the order of these 2 frames in the stack order? Probably it's quite straightforward to reason that the one that on the left the order is correct, and on the left the order is difficult to predict because we just don't know. We don't have here some information which would give us a clue what comes first. In the left case, we know that probably first you have to do coffee, and then you put the milk once you've already done coffee and put the coffee in the cup. Now, so the idea here is to use this intuition for to say that if we can learn an algorithm which will predict correct order, these frames are likely to be the actions. If the frames in the algorithm cannot figure out what order it is, the frames may not be the action. This is a hypothesis. Well, let's see how it works. Well, that's actually 2 hypotheses. First is, can we learn the order prediction at all? How will it be? And the second hypothesis is, will it actually be true that if we predict the order, then the fact of this prediction correspond to action. So let's see. Let's see first how we can learn. So here is a formulation. So it's neural network SAM is architecture where we have where we subdivided the video into x1, x2, xm, so segments, and then we randomly sample a pair of segments. We give it to the network with some features. We have the features and not mentioned. And then there are 2 things. So first is a network as actionness, and then there's another network which actually predicts whether these 2 segments, x and xj, whether they are in correct order, in a forward order or backward order. So of course, because they are given in original videos, the order information is free. This is also written. So what happens in the f-box, and what is W? So W, so it is just a classifier. So it's a classifier. On the bottom is the loss. So it's a basic binary classifier which will say two frames or 2 segments of the video they are in a forward or backward order. And S now is can think of it as, well, it's a weight function which tells should the network actually trust these 2 frames, or are these 2 frames not discriminated out to predict the order. So S essentially it's it provides the confidence how likely, how well can we put the right information from the segments X, I, and X, J. So now that we don't have any supervision for S, for S, and this is given from the auxiliary task of learning F for the verification. Then at the test time, actually we are not using F at all, so one could use maybe F for some other tasks, so F is just an auxiliary task. At test time, what's important for us is the S function, which gives confidence out, and what important also is that it gives you confidence for each individual segment. So it's not a function of pair of segments as F, it's a function of each individual segment. How likely it is, how confident F should be about trusting the XI J. And what you see at the bottom is the S function for a particular video. So you see some both examples where the person is standing and doing nothing, the S is low, the person is putting something in the cup, it's up. So actually, it looks like it does something. So let's simulate it more rigorously. We train on the largest set of them, scratch object, and emulate on two datasets, coin and gross task. Gross task I described before, and coordinate set representation. And we are using retrain I3D features, which are also trained without manual addition. First, just predicting the frame-wise, so that the S function actually can predict the yes or no for action, not action, given annotation in the coin and cross-out datasets. And so the action was trained without integration. Coin and cross-task, of course, they have annotation of some very specific actions. There are some baseline chance GDP03 is discard and videos because they usually they're not interesting and actually confuse the method if it's handmade. And then there's also an untagged and flow, which basically measure if the frame has a hand or if the frame has much motion, and as you said for such frames, there is no chance to these frames have no chance to be actions. And the numbers in terms of fabric precision. So you see that our method outperforms lines with by time margin, and also it approaches this right design. Nice. So out of the previous numbers for frame-wise equations, so here's a bit more difficult task of temporal action situation. So in several methods for doing this. These methods are supervised. So we do curve on top. So we see that our red curve is approaching the supervised method and fitting all the other baselines at the bottom, which are unsupervised. Actually, the green is kind of supervised because it uses the green temporal prior baseline samples, action proposals from distributions, from a distribution which was estimated using round truth, so it's not quite unsupervised. And so here, last result, where we show that using action as chamber method actually does help to other methods which try to solve actual action discovery. So I've shown the action discovery in cross-out dataset, so this is the reference 2 in this table. So you see that adding the actionness to the previous method does improve the results as well as into other papers. So the actionness doesn't give a huge boost, but it is complementary, and the fact that it actually works without any supervision, and the hypothesis which I said, actually two hypotheses which I said at the beginning, that first it's possible to learn the order to some extent, and that the order does predict the action is just, and you see here that it does do some some qualitative results more can be found on the page. So here you see that once the person starts the action, the blue scores, so the blue curve reflects the S score, and the green intervals correspond to the action graph shows. So you see here that the green and the high values of blue, they are quite correlated, and once the video gets to the green segments, we also see that action happens. All right, so I have still quite a few things to talk about. So let's move on to the next question: how to learn visual representations which rely on manual annotation. We want now to still continue working with the instruction videos, as they seem to be very rich in terms of variety of tasks, variety of tools, and execution of these tasks in single task. And we want to scale up the data sets from the cross tasks that have about 83 tasks. So here we want to do much larger. To help us with this, we use WikiHow. WikiHow is a source which is not easy resource, common resource to describe how to achieve different tasks. So these tasks are very diverse. How to retain, it could be also how to improve your girlfriends or how to meet your future husbands. So not all of them are interesting for us. So we do have a manual filter of one level of just the tasks to go through. So the WikiHow has lots of tasks. It's grab 130,000 books. And then just by the name of the task, we hire people and we run through this 100,000 task name and just say that which ones would be interesting for us, which not. So that's quite a limited foundation, but which just helps us to deal with better with noise. Maybe it could be done automatically as well. We just wanted to eliminate some noise, so that was not much of work. So apart from this, everything else was done automatically, and what we ended up with is 23,000 tasks, which were computers. And since then, so we've collected, so we took the name of the friends, we took and collected videos, so collected 1.2 million of videos, which are typically narrated, and then these are long videos of maybe 10 minutes long. So once we got the videos, narrations, narrations, and we also, narrations that we divide into sentences or parts of text, or each piece of text, isolated piece of text, also define the short video segments, and this is, so in these data sets we have 136 million of short video segments. Starting this. So here's this graph distribution of topics of the tasks in this data set. You can see it's quite diverse also with still food. So that's a natural diversity of what people put on the internet. Here are some examples. And here is the comparison, just in terms of the size of the data. Some of the data sets, most of these data sets, they have manual annotation, so they manually verify, either manually created or manually verified annotation. While our data sets is completely collected automatically, however, our data set is about 1,000 times larger than system ones. So let's see what we can do with it. So here's the, I'll describe how to learn on the So what we would like, the goal of this work is to learn visual representation, for videos. And the way we're going to do this is to try to learn inventions, which brings text and manipulate together for corresponding video segments. So remember, we still the instructional videos, we collect them in the way that the video clip has corresponding text, which comes from transcripts. Of course, this text is not perfect because it might be the transcript, the automatic speech transcription would be wrong, but there are many other things. And so one triple problem which happens with narrations is that people not just describe what they are doing, they are also describing everything. And more importantly, the time when they describe what they are doing may not actually coincide with the time when they're doing it. So if we just assume under assumption that there is a perfect or roughly perfect alignment between the action and text, we would be ending up with this video describing flashcards, maybe some oregano, while more relevant options for these videos would be spinach and give it a couple more doses. So let's now to figure out where is the action correspondence. So to discard the wrong corresponding text and find out the corresponding. Right, so we'd like to some formulation which will help us during training to figure out which text does correspond to video clip and which text does not. So this is formulated as a, for instance, learning NCE, where we have first we have view input and version input x, y, and we put it into the NCE formulation, which has been recently very popular in showing good results. But we also went into the multiple learning strategy, where so at the top of this expression we see sum of all pairs x and y which come from the same video. And then we also have at the bottom we have a sum of negatives where x and y come from different videos. So we are not, as we have a sum here for positives, we are not restricting that particular x one to particular y. We're just saying that the sum should end up doing something. Okay. So I already said that something was different days they come from the same video and different days they come from videos. Alright, so now how do we train the model? So importantly now the model is trained from scratch. So we are not going to move away and try to see what can be done without any pre-training using MIL-NCE data, just ImageNet or kinetics. So our models are trained from scratch, just from the noisy, just from the videos and noisy narrations which are provided in corresponding within the instructional videos. So the architecture is here. So we have the CDCN for the videos. We have 32 frames to input and frames per second. So it means that we are right. So we have for text we actually here we just do some very simple standard word to vec embedding and few linears and non-linearities, and so that is really standard, so nothing specific new here in architecture, and we get two embeddings, so size 5 to 12. We also train some models with small embeddings, also works. And then we have, on top of this, we have our proposed MIL-NCEs. So the evaluation is done on several datasets and several downstream tasks. So action recognition, action representation, and text retrieval. So before going to the results, we first collect the benefit of NC and C. So of course NC could be substituted by something else. For example, partial loss. And so here's that confirms the findings from recent findings that NC loss is good. And also extension to MIL-NCE is actually important. So if you don't do multiple design, then the alternatives perform worse in most cases. So this evaluation now in terms of absolute numbers. So I'm trained for the full 100 data sets. So here's how for you to zero-shot video retrieval. What does means that so here the results the first we can do. So the green one is retrained system network, retrained machine and genetics model. And then and then evaluate the retrieval. So if you take the network which was retrained on idle notation, fine-tuned on YouTube, so you can do as a training test speed. So if you take the train speed and fine-tune it, so you get this result. And so it's very interesting. So imagine that if we use our methods trained only on how 200 and dataset, which has no annotations, and in this case we don't even fine-tune on book 2. We do not outperform the two other methods by the margin dataset. We don't need any manual annotation there, and all this is much better. So in conclusion, one is that the representation must be good, which we learn on the video, and it's even so good that we don't have fine-tuning. Although it should be said that the utility set is similar to how to on them because it's instructional videos, so they are kind of in the same way. Although the training videos do not include the videos. So for now for the action recognition, so here are some comparison to state of the art for self-supervised video representations. So we are doing quite well, and also even compared to fully supervised representation on MSRDTT on Core and YouTube. 8 million and cross-task, so we are up to other baselines. The data is available, and the models, our representations are available online in PyTorch and TensorFlow formats. We also provide a demo, online demo, where you can just type any text query and search in YouTube to data sets using our representation. So we hope that this representation could be useful, and we are eager to see how other people are using it in their projects. Right. So that's about the first part, which is about analyzing the embedding from instructional use. So now I want to talk very briefly about the second part, which is more bodies and vision. Still, it's the story quite well because the part is going to build 3D categories. So here, in instructional videos, we were analyzing the videos and trying to figure out what is the composition of the task in terms of actions. So here, we want to discover other actions which lead to a particular goal. So it's going to be a reinforcement learning and reinforcement learning smart rewards. So in a schematic terms, so we are providing to the algorithm information what is before and what is after. And so ideally in the future you want the robots to seeing just a picture of a shelf here. We wanted to figure out how to construct it, or even more imaginary if you have a house and you want to renovate it. So just to imagine the picture of how you want it to be, and then the robot goes to the shop, buys things, and constructs, makes it true. Of course, we are trying to do things much simpler. So it's still something to this add-on. Also, what we want to do, given a particular shape, for example, an arc, we would like to construct it from different sets of primitives. And by different sets of primitives, I mean different shapes, but also different shapes also. I will show in a second what I mean. So as inputs, so we are given one instance of a shape and also a category classifier, which will tell the once the algorithm builds something, it will tell it has built something useful or something like this. So the method is divided into two parts. So the first part is later in stage space. And the second part is learning from the policy which was learned. On the left, it learns, so the left part learns state policy, and the right part learns visual policy. So first, what I mean by learning state policies? We have, let's say, we have an instance, this type instance of an object which is already composed, and we just try to decompose it. We call it unmix. We try to decompose it in different ways. Remembering how we decompose it, we learn the value function. We learn the value function, which is in reinforcement framework, and using this value function, we try to construct new instances of NAR. So what you see on the left, so the arcs are different. So the shape is the same, but the composing parts are different. And that's what we do. The learn value function helps us to discover the new instances, and then we unmake these new instances and learn the value function and iterate them until we get a good set of, until we discover many different sets of the shape composed from different units. Once we have this, once we have the policy which can construct an arc or in the state space, we learn visual policy which will mimic this state's policy. Why we want this? We want, actually we don't want to estimate the state of the world from visual inputs. It's hard for our problem with an object of making state by itself. It's probably, really, it's often harder problem than actually predicting the direction. So if we do, we don't want explicitly reconstruct the world. We want to, just from an image observation, learn policy that given an image observation will directly provide action. So how it's done here, so we already have a policy in the state space. We generate images, we synthesize images, we know the actions it should be taken for each synthesized image, and we just run a policy which mimics the state policy given the image. So here are some results. So we are learning the policy to construct arcs of different heights. You see here from left to right, so we initially that's what the camera sees, the robot. So it sees lots of primitives, and it has to figure out each part to take, where to stack them, and so it arrives to the correct shape. So it was trained, as I mentioned, so it was trained purely in the simulator, so it has never trained and has never seen the images. The user seemed to real transfer to help us, so from using the paper, which we published last year. And now also, besides that we go from sim to real, we also go for cubes. So the system was just trained on cubes and parallelepipeds to other objects, and as you see here, it works well. And now I'm going to show also video of constructing arc from primitives, and it's not only constructing arc primitives from table, it is able to adapt to the new situations. So here the person using new primitives on the table, and so the policy without explicitly reconstructing the state of the world, it understands that what it should do. So it disassembles parts and assembles in your arc. And this happens because well, the objective, the reward which was given during training says that all primitives which are on the table should be constructed arc. That's what it tries to do. That's what it is able to do, even if the arc is partially constructed. So here's an example where it uses very different primitives than what has been used during training. So since we use a RGB camera here, actually, I think just that camera doesn't care about the exchange and color, but it is to good extent invariant to different shapes of objects, as you can see. Alright, so I'm all done. So let me summarize. So I talked about two directions. One analyzing videos and textual videos. It's a challenging problem. There's lots of things to do, large space to explore, and related actions. It's the sequences of actions, many examples, here with conditions. What I think is that though this data is noisy in terms of narrations, we were able already to learn representations. A representation outperforms the other visual representations with video with minus vision. However, so if we are interested in, for example, application of automatic visual assistance or robotics, so these videos are very interesting to analyze, but they do not provide for other cases. If you want to robot to do something, it needs to learn on errors. And there's a problem of these instructional videos that they will only show things. The parallel directions in robotics, it's almost the opposite, because if you want to start a robot, there are failures to learn from. So that's very good. However, these kind of methods are not sample efficient, and that was simulated or limited environment. This limitation to simulated and limited environment is quite a strong one, I believe. So the condition, we know that going from the lab to the real world requires analyzing real data. And for robotic, it seems for the moment is hard. So, but I believe that the future should be a strong interaction between these two lines of work. We combine the advantages of both, so we will be able to learn from large-scale, realistic, and diverse data, which is YouTube or any other kinds of videos, and we will be able to transfer this knowledge to robots and validated knowledge which we have learned. It actually opens for new tasks. Because just analysis, we can analyze and come interesting measures, but before we try it for real, we will not know if this what we have learned is actually useful for performing real tasks. So that's it for me. Thank you very much for listening. I hope you enjoy it. This comes our HM demo and what's called the Multimodal.